Yeah, okay. Oh, actually, if I can hold it, maybe I can just stand in front.
Okay.
That'd be easier. Okay. So, as I introduced myself earlier, I'm Aaron. I did this work with another name that may be familiar to some of you, Oscar Hernandez. This is part of an ongoing work that we've been looking into on message aggregation. So let me focus on what got us here. So basically, the partitioned global address space model is popular as a sort of natural way to map the classical shared memory programming paradigm to distributed clusters. But the side effect is that a number of applications or the access patterns that they may employ have some challenges in mapping their operations to modern hardware in an efficient manner, particularly that certain irregular patterns that we may see have the tendency to produce really large numbers of really small messages, which can congest the networks, particularly for things like graph problems, data analytics, so on. Previous efforts that we've had kind of addressed a way of approaching this in applications in a low overhead kind of fashion, so that applications could be modified as minimally as possible, trying to reduce the intrusion, but while still gaining better efficiency. What it was doing was it would basically have an implicit aggregation strategy where so long as the programmer is willing to relinquish some of the constraints on completion semantics, their operations can be automatically held onto and deferred for an unknown length of time and completed later in bulk. But while it was proven to work, it was never really proven to scale up to large systems or to be portable across multiple architectures. So that's what the focus of this talk is going to be about, is trying to look at does this stuff scale and how well does that scale? Oh, there we go. So a little bit of background first before getting into it. This work is based off of a couple things. There's something called the Bail effort, which it's not it's not just one thing, but basically it's an effort that exists to identify some of these key challenges that I have referred to, different patterns of interest, and that we have high interest in solving. But also then to provide a few different aggregation strategies, libraries that can be used to sort of address these concerns, one of which is the only one we're going to be focusing on. It's called conveyors. And it also provides implementations of applications employing these different patterns with each of the different versions, without aggregation or with one strategy or another. Conveyors themselves are like stateful two-sided queues, so we break some of the one-sidedness that we're maybe familiar with too in this space, but they're relatively simple queues in terms of the user interface. You push to them, you pull from them. Their progress is more or less out of your hands, although the conveyors themselves, you do have to still manage that explicitly, and that's one of the things that we take away with the extension that I referred to before. So specifically, our work was designed to be more widely applicable, but we specifically latched onto the OpenSHMEM PGAS API, and we introduced a extension to it that we called aggregation context. That basically being that when you want to do point-to-point operations to send a message to a remote node or do an atomic update, you then just provide one extra argument for a communication context that you'll use for that, and that you specifically specified you want aggregation on. and then it will take care of the rest. That's how you get the loosened completion semantics I referred to, but the consequence is that the only way to ultimately guarantee at any given point that a operation that you issued is complete is to flush out operations by calling what they call a quiet for that context. However, you can still at least use your input buffers immediately upon return. So internally, how they work is that information, metadata essentially about the operations you're performing is encoded into a series of fixed size packets. That's a restriction of the underlying conveyors API. These fields include things like the operation type, so you can later determine how to respond to the packet. Any remote local addresses, a value like for a atomic update or something. And for efficiency, operations with particularly low encoding requirements that might only use like, one field out of the packet, also can get an additional level of deferment to be packing multiple of those into a single packet, so that we only call to the conveyors API once. And progress of the contexts is completely managed internally. So up until the point you issue a quiet, you never have to do any kind of progress management to advance them. Just kind of automatically when they fill, they'll complete. Just to kind of give you an idea of how they look, so you can see how simple they really are. This was the design concern. So this is basically a normal OpenSHMEM application, just doing an atomic increment on a remote location, and then after we process all the updates that we have, we do a barrier. All that it looks like to aggregate this in the background is we create one time the aggregation context at the top there, and then we have that same atomic operation that we basically just add in that first argument, the context in. We add in one extra line for the context quiet, and that's it. So that's the simplest example showing how to update it. But in our initial results, just doing that was able to get up to 65 times performance improvement on certain architectures. So what we just looked at was something called histogram. That's one of the applications from Bail. So let's look at that a little bit more, because that's going to be the primary focus for our scalability testing. It basically represents a communication pattern where all the different processing elements, or PEs, are asynchronously updating random remote locations and memory locations throughout the network. And to do that, the benchmark is basically just generating a uniform list of those remote locations in the distribute table, and then it proceeds to do what you saw earlier, just simply have a tight for loop, update them all, and move on. This is the simplest and most direct indicator of the underlying performance of aggregation context, so that is what we're focusing on here. Basically, if a micro benchmark focusing on this kind of pattern doesn't work and work well, then nothing really will. Okay, so we have a number of different experiments. Most of them are focused on the Frontier supercomputer at ORNL, and that's so we're going to be showing a number of different runs, but some of our runs went up to as high as 8,000 nodes. That's for a little bit of information on the cabinets themselves. That's 128 nodes in each individual cabinet. Each one has one 64-core CPU and Slingshot 11 NIC with 4 ports, each with 200 gigabits per second. The performance portability that we'll be doing compared in 2 extra platforms, being ORNL's Andes and the HPC Advisory Council's Iris. The former being a system with dual socket, 16-core EPIC CPUs and NVIDIA ConnectX 6 InfiniBand. which is also the same kind of card, just with a different bandwidth and version number that Iris is using with its Xeons. All the testing with histogram was done using weak scaling, so perfect scaling being flat lines, that's what we would want to see. Also for the OpenSHMEM implementation, so this is something that has multiple different implementations we could choose from, but we chose the 1.4 version from OpenMPI. There's two different versions that we had because we wanted to be able to compare against the original numbers we had from the first paper that was on Iris, so it's using a slightly older version. But the two key metrics that we're interested in here is we're looking at the speed up of aggregation over non-aggregated, and the raw total aggregate number of remote updates per second that we're able to achieve. Okay, so here's the first test that we have. This is scalability, so this is all just frontier. What we have is 1 to 64 processes per node on node counts ranging from 32 to 512. And what we have on the left is where we're looking at, this is unmodified straight from Bale, where we have this method implemented with VIA conveyors. And I don't think I clarified it before, but to be clear, one of the reasons that we're not just simply using conveyors themselves is because it's a lot more complex to actually use than I was getting into. So I kind of glossed over that a little bit, but we made this interface to be a simple, easy to use layer on top. But then that means that since we are built on top, we expect to be relatively similar or maybe a little bit worse, but that's part of the sacrifices that we see. What we actually see, though, is that here we're pretty much neck and neck, which is very positive to see. And that is, I don't know how many, I'm not good with the mental math here. I don't know. It's 512 times 64, if anyone wants to do that. That's, okay, so, but the scalability is, in terms of speed up alone, is not sufficient to tell us if it's really performing all that well, because the non-aggregated approach may just be really, really terrible. So we also wanted to see just kind of what the raw message rate might be, and we saw that that was also, fortunately, that was also fairly positive and fairly stable all the way through. And it's worth noting that we see these lines way up at the top that kind of stand out. Those are the one process per node numbers. So basically what that's really meaning is it's saying this is what happens when we're requiring that basically every single remote communication operation is always going across the network. That's the distinction that we see. In anything else, half or more of the remote operations may potentially be actually going to the same node. I mean, it can vary a bit more there. So we know that the scalability itself, raw scalability itself, looks good. So we wanted to be able to know, how does this look across different architectures? The red and purple lines are showing what our original results on the slightly older Iris hardware were able to achieve. And we note that in particular, the speed up is kind of dramatically larger, which might initially suggest to us that maybe our performance is kind of falling behind a little bit on the newer systems. But when we look at it a little bit closer, basically what we realize, especially with Frontier, is that the network hardware itself, and this is a good thing, but the network hardware itself is actually just getting a little bit better. at handling the small messages. So the non-aggregated approach is able to just perform a little bit better. And then the room for improvement is a little bit slower, it's a little bit smaller, but as we can see, it's still very dramatic. And similarly, we see a pattern with Andes. Andes and Iris are the two InfiniBand versus Slingshot on Frontier that has a lot more dynamic aspects to it. It's got congestion control, quality of service that we don't necessarily see the effects of on the InfiniBand side. Make sure. Okay, I think I'm good on time. Okay, so one thing I want to be able to touch upon a little bit. So I mentioned earlier that we ran up to 8,000 nodes, but if you were paying attention, you may have noticed during the scalability plots that I showed earlier, I only showed up to 512. There's a couple reasons for that. One being that we performed our testing at a couple different times. So our initial testing ran up to 8,000, but then Cray engineer came along and said, oh, we just produced this new version of our core network APIs that you're using underneath the hood here. Why don't you try running again with this? But running on 8,000 Frontier nodes is very expensive if you've tried to do that before. So we did not. We were satisfied that we already proved that it would scale. So we just wanted to know, do we see a difference from the newer software? Bottom line is we didn't necessarily see the differences that we expected. What we ended up seeing instead was something a little bit more interesting. So basically, what we're seeing here is actually not the old versus new in terms of software so much as the old versus new in terms of scheduling. Because when we were running the original jobs, we had exclusive access to the system, and we found that running the exact same. I should clarify. When we did this initial testing, we found we weren't seeing a difference between using the newer version versus the older version so much, but then we tried using the older version to compare with the older version, apples to apples here. But what we saw is basically when we would run the same setup with shared access, so that we were only using, say, 32 nodes. Okay, then we had dramatic drops in performance, and that's an interesting note because on the Frontier system, which we may potentially see a little bit more of in the future, there's less control that we have over other jobs that are running the system, but we are able to see that clearly they have an impact on performance. This was the same thing with contexts, so it's about double the change. So one other thing we looked at just a little bit, we wanted to know how efficient the aggregation was. So this was just a very simple test that we did. Basically, we took the OSU non-blocking put micro benchmark, and we just modified its buffer sizes to be the same as what we were using internally. So we wanted to get something akin to a maximum performance theoretical peak as we scale up the processes per node. And by the time we actually fill it up to 64, we see that it's actually not all that far off from the theoretical peak by that point at least. So we can be rather satisfied with that. In the interest of time, I'll go ahead and kind of wrap this stuff up. So what we saw is that we were able to determine that our methods are indeed highly scalable with very minimal difficulty to the application developer for porting their codes. That was up to 65 times on InfiniBand hardware and up to 15 times on Frontier's Slingshot. Additionally, in some cases, we actually noticed that our performance was able to even exceed that of conveyors a little bit. So I think I kind of glossed over that a little bit earlier, but basically what we saw is that the fewer calls to the conveyor API from that second level of deferment I referenced was able to actually be enough to even gain a slight edge over it. But it could also be, the same strategy is implemented at a high enough level it can be applied to other models. But future work in particular could really go in the direction of deferring associated general code along with the network code dependent upon it. Questions?
Thank you.
It would be neat to get a reaction from Vivek.
Okay. I get to answer the first question every time now. Thank you, Aaron. Thanks. For folks who don't know, on the runtime side, this is so challenging to even get like 1% improvement of performance. You try out IAUT, performance will be great. So we have multiple group members, user, zero, ex-former group members, Max, who worked on this kind of stuff. So I don't know if you're aware, Aaron, but we've been building this actor runtime on top of conveyors. Mm-hmm. So I'm just wondering how much of this 40% improvement can help our actor runtime as well.
I think if I recall correctly, I believe that the actor runtime that you had was designed to be, strictly speaking, was designed to be a little bit more flexible, for doing basically whatever you want to do. One of the ways that we were able to achieve the kind of performance improvements that we saw, and at such very small effort level, is because we were benefiting off of the assumption that there's a very limited and set API, set number of operation types that we know at compile time exactly what their behavior is going to be. And that's how we're able to do all that without programmer input. At the same time, if any of the actors were doing something similar internally, where they were using a fixed set of operations, then you may be able to apply the same kind of strategy there. I guess actors would just then still stay at a slight abstraction level higher for what it allows the end user to be able to do.
Any other comments or inputs? Please. Oh, so now we need more microphone.
Yeah, great talk. Thanks. So I think my question is more for the future work, and I'm just wondering whether it's feasible to extend your work to support GPU, probably with NVSHMEM or something like that.
There has actually been some interest in looking into accelerators, and in fact, it's actually been a lot of interest in particular in not just GPUs, but looking at what may be possible for going into like SmartNIC spaces. We have not, unfortunately, been able to actually go into that yet, though. But that is something that's been on the table for future work.
Future
so
work on GPU.
It is future work, yes.